Thank you for joining me. So today I'll be talking about learning Jacobians for robotic control. This is based on a presentation we gave on some recent work we submitted to the International Conference of Robotics and Automation. Um, so here's an outline of what I'm planning to talk about. It probably seems like a lot of things, but there's a lot of important background information that will be useful to kind of put into context what we were trying to do in this direction of research. And then the second half is what did we actually do in this paper that we submitted and that was accepted. So to kind of give some general things. So first off, we're going to need to define some important factors about robots. So we have here an image of what is called a Kinova Gen-3 light serial manipulator. It's what we used in our experiments. And so an important thing about robots is we have this concept of joint angles Q. These are the variables in our serial manipulator, and these are the things that allow us to move the robot around in space. Then we have this idea of what is called the end effector, which we're defining as X, which is just the location of the robot tooltip here. So that's why I put it at the tip where the gripper claw is. And so when we talk about what kinematics are, without going into the mathematical depth and understanding the underlying things, kinematics is just these equations or these functions that explain where the end effector is in 3D Cartesian space or 2D space, depending on where your robot lives, as a function of its joint angles Q. So for the sake of this presentation, that's all you really need to know. We don't need to know and dissect kinematics further, but just to give you a high level understanding if you're not familiar with robotics. The next thing that we're going to need to know about is what is robotic motion, at least from my understanding of it. So the motion of a robot can be described with the following equation. So the velocity of the end effector is then equal to the Jacobian term with respect to the kinematics times the velocity of the joints. And so what a Jacobian is the partial derivatives with respect to, I think, a vector function. I think that is how you would describe it. If I'm wrong, please let me know. Just want to make sure that I understand it. Yeah. And so unfortunately, in practice, in robotics problems, calculating the Jacobian can be difficult for a number of different reasons. The first reason can be because there's uncertainty in the modeling of the problem because of the kinematics or the dynamics. So an example of what this might look like is where we have here a unknown object that is being held by the robot. And for some reason, we've defined our end effector to be, say, the tip of this wooden spoon. But we don't know anything about the wooden spoon, and so we haven't mathematically modeled it. And so we can't derive an analytic Jacobian for this term, even though knowing it can be useful for solving problems doing control with robotic systems. This also more practically can also arise in what is called image-based visual servoing, where that domain is you have a camera, you can see the robot, you're tracking some points in the robot, and there's some point in the camera space, and you want to move the robot using just the camera information. And unfortunately, the analytic Jacobian that exists for defining stuff with respect to the camera has dependency on depth, which requires you to approximate the analytic solution anyways. And you also need to know information, the model parameters of the camera, which can be difficult because then you have to do camera calibration. There are other ways to solve it, but these are just potential issues that can be with deriving analytic Jacobians. And so at some point, we're going to talk about how we're going to approximate this term. But to kind of put in the context of okay, so we can describe these equations of motion. What are they actually good for? So the problem that we explored and did our experiments on is the task of reaching, where the idea is that we want to find some joint configuration Q star that moves the robot to a target location X star. This is just inverse kinematics. If you're familiar with it, if you're not, that's another way of describing reaching, is the inverse kinematics problem. And so if you know this Jacobian from these equations of robotic motion, you can basically solve the task. And this video here is, if nothing else, that's basically all we did in this work. Yeah, so how do we control the robot using these Jacobians? Well, so in control literature, the way you might go about doing this, instead of using, say, a reinforcement learning approach, is you just do direct optimization against the functions of that you know. And so what we could do is that we're going to find some Q star by just doing a minimization over the joint angles themselves and minimize, say, the mean squared error like so. And so if you wanted to kind of put it into maybe a control loop setting, you can define it kind of something like this, where, in the first step, we calculate our gradients, which I'll say is taking an action with a policy or something. And these are interpreted as joint velocities. I'll explain what all these terms are and where they come from slide in case you're confused. And then we just send it to our environment, which is moving the robot around. And then this is basically, in some sense, just running gradient descent on the joint angles to find this position. And that's the way you can solve it. And so in like robotics control, one way that you can do this is with what is called the inverse Jacobian control law. So instead of solving it as, Rn to a single optimization function, we'll solve it as a system of linear equations. So we define a system of equations to try to match the kinematics end-effector locations with the target position x star. And this is then solvable with Newton's method, which is the whole point of Newton's method, is to solve these systems of nonlinear equations. And so that's where we need this Jacobian term as part of Newton's method, and that's where our equations of robotic motion come in. Oh, look at that. We need the Jacobian term, and we have a way to get it. And so this equation here is, again, just kind of repeating what actually are the steps in order to apply this method on this problem, at least as I've come to understand it. And so, these joint velocities are just being decomposed so that we can kind of see the rates of change, I guess, of the kinematics function. Yeah. So that's kind of the high level background of the problem that we were using, like doing something. So we know there's some issues with Jacobians, but we haven't explained how we might approximate them. And so kind of that's where our research paper starts to take over, which is kind of what is the fundamental research question we were looking at. And it's basically, how can we approximate Jacobian terms to be used in doing these kinds of control tasks? And so there's a lot of previous work on this topic, particularly in the area of visual serving, which was the angle we were taking looking at this problem. Question?
Excuse me, Michael, don't you really want the inverse of the Jacobian rather than the Jacobian?
Yes, technically we do really want the inverse.
Thank you.
Yes, yeah. That is actually another way people have thought about solving this problem in visual servoing, where they just directly learn the inverse. We do, yeah. I have, yeah. We actually, I'm just going to leave it at that. Yes, we really just want the inverse, but for some reason we thought it was good to learn the Jacobian instead. That I'll explain a little bit where we talk about incorporating. Now I'm just rambling. Sorry. Thank you. Yeah, so there's lots of previous work on this topic. Local approximations are basically, we take a finite approximation, the immediate pose of where the robot is, and we can do like an online update with Freuden's update to make it like useful and further away from where the initial approximation is taken. But unfortunately, this only gives you an immediate approximation for where the robot currently is. And so you can't use it across like moving to the other side of where the robot moves in space. So then the previous work in visual serving looked at maybe global approximations methods through like doing a multiple local linear k-nearest neighbors approach. Just by the words in that, without explaining how that method works, it's a high memory cost because we need to hold on to all of the data we have because we're going to need to use the k-nearest neighbors. And it has this expensive online computation cost because in that vein of getting approximations, you need to fit a linear model at every point that you would want a Jacobian. That could be kind of expensive, especially if you have a large neighborhood, which is required to get a good approximation. So our proposed solution is let's just use function approximators. Neural networks are great. I'm kind of a deep learning guy. The nice things about these, they're parametric. I know some people say they're non-parametric, but the way we did it, the number of parameters is fairly small. It's a global method in the sense that, we give it the joint angles Q, it'll give us a Jacobian approximation, and it can, work for large portions of where the robot might be able to move. And theoretically, if we had enough data and a big enough model, we might be able to recover the true Jacobian, which could be a good idea. In actuality, it's not, but that's, I'll say out of scope, but if anyone wants to know, I could talk about that point as well. So that's kind of the question that we were interested in looking at. And so how do we go about using neural networks on this problem? So we had two approaches, the neural Jacobian method and the neural kinematics approach. I'm not very imaginative in my naming of things, but anyways, so the neural Jacobian method is we're going to take a neural network and just directly predict Jacobians as the output of this network. And since we need to somehow, we want to really, really define a supervised learning problem for this. So the way we're going to do this for this approach is we're going to apply the secant assumption and say, for itty bitty changes to the end effector locations and the itty bitty changes of their corresponding joint angles, we can basically say it's the same thing as our equations of robotic motion. And so if you're not familiar with the secant idea, we're just trying to draw a straight line between our functions, which might be really curvy. And so this doesn't work for really far away points. For nearby points, you could say it's roughly correct. And so what this leads to in terms of like something that we run supervised learning on and do regression is we just kind of take the k nearest neighbors again from previous works, and for each point in our training set, we find their neighborhood, and then for each training example, we're going to fit this approximate Jacobian term to try to minimize the relationship of our equations of motion. So the first measure, like the first part of our loss term, is kind of been used in previous works where we're just doing it in the measurement space, which is just, we want the rate of change of the end effector to be equal to that j times q dot component. And then we also added this inverse term, kind of as Rich was mentioning, that like, don't we really just want the inverse? Like, well, we did kind of look at that, but yeah, and our intuition for why we did this was not necessarily because it was what we wanted. The idea of why I proposed it was, well, we'd like a j to be invertible. So if we explicitly enforce it in our loss function, that'll discourage it from not being non-invertible, which could be all sorts of problems. And we had some mixed results about how useful doing this motor space fitting actually was in practice, although I don't go into that detail. Basically, as you have more information you're trying to like match up, if it was more useful than when you were like trying to under-constrain the problem. So here's kind of the training loop, fairly simple supervised learning problem. Collect your data set of interactions of joint angles and effector locations, find the k nearest neighbors in this joint space, and then calculate the finite differences for each of those corresponding neighbors against each other. And then just perform mini batch updates to kind of do on the finite differences between neighborhoods in order to train this approximate Jacobian method. Yeah. And so at deployment time, when you want to solve the reaching task, you just pass in your joint angles Q through this neural network, and it directly outputs a Jacobian approximation. So our second approach, which we call the neural kinematics method, is we're going to just train the neural network to directly predict kinematics. And using this, we're going to then use backpropagation through this approximate kinematics function to get the Jacobian like implicitly from the approximate kinematics function. And the kind of intuition for why we thought this might work is that neural network theory, doesn't only learn how to predict functions, it also learns how to predict derivatives of functions. I think actually formally it's like nth order derivatives are well approximated. And so like if you take away the robotics context, we're just kind of seeing how well this works in practice, but it's interesting again for robotics people because you know robots with this. And so to kind of explicitly spell it out of what this might look like in practice. So here I have an example of some small toy experiment I ran where we trained this neural network to predict the sine function. So it only saw the green line at training time. And then by backpropagating through the inputs of the neural network's prediction on the sine function, we see that this blue line, which is the neural network's predictions, does seem to recover the derivative function of the sine function, which is the cosine. So, based on this, it gives us high hopes that we can approximate the Jacobian for higher dimensional spaces. Yeah. And so at deployment time, this is a bit more involved than the neural Jacobian method, which just needs a forward pass. So first off, we need to calculate the approximate end effector locations. And then we just use backpropagation through those predictions again to get this Jacobian to our control. Yeah. And so that's basically all of our methodology. And so to kind of summarize and put things in the context of what we did to experiment with this stuff, here is a bunch of pseudocode to kind of summarize everything that we did in terms of evaluation of how well these methods work in practice. So our work is basically all this blue text where, we do one of our two methods. In this case, we would do the neural kinematics approach where we just say our data set is X's and Q's, and we take minimize the expectation with respect to the data set of the squared error loss. If the notation looks funky, let me know. I think this is, I like to think this is correct, but I'm never 100% sure. And then we just apply taking the back propagation trick through the forward predictions of this approach. The second one maybe also outlines maybe a bit more clear of what we did for this alternative method, the neural Jacobian method, where we start with an empty data set, and then for each training example Q, we find the nearest neighbors, we take the finite differences for that neighborhood, separate them, and then we add them to our data set, and then we just train on that collected data, and our approximations are directly forward pass. And then our experiment loop is kind of this pseudo control like thing where we take our action where instead of using the ground truth kinematics Jacobian, we now use the, okay, now we use the approximated Jacobian as opposed to the ground truth one. And then we just update our environment based on these actions. Yeah, so fairly, I think, yes, fairly straightforward. And so to kind of close, we just to show some videos of some experiments. I didn't think looking at tables would be all that interesting, so I'm just going to show a bunch of robots moving. So to kind of set up the experiment. So here we have the Kinova Gen-3, which is what we conducted our robotics experiments on. And the idea is basically exactly the reaching task we talked about at the beginning, where for this task, which is a visual servoing task, the target and the position of the end effector are defined in the camera. And so we're doing tracking, I guess. And the idea is we want to move the orange dot to the green dot here. And so in that case, this is like a two-dimensional problem. So when I'm talking about features, it's literally like the x, y, and z coordinate if available of the points in space. So the visual servoing task was just 2D, and the kinematics, the robot space was 3D. So here to kind of separate, so these three red blocks are our method that we proposed in the paper. Where the bidirectional neural Jacobian is fitting both the inverse and forward relationship that we talked about, and the neural Jacobian only fits the measurement space loss term. And then the blue one is this alternative method previously proposed. And so here's kind of what the culmination of all our work looks like in practice. All the methods are successful for this particular target, although the bidirectional fit moves slightly differently, and they all roughly move towards the target. Yep, and there you go. Lots of hard work to get that. And so, yeah, uh, yeah. So, okay, yeah, I just want to go to my next slide. There we go. Okay. So then here's video footage of our kinematics setting. So in this image, the target is roughly positioned where these orange boxes are, and we replayed the trajectory inside our simulator so that we could actually see where the targets are and make it clear that the robot is reaching towards the correct spot. So this is using one of our variations of this neural kinematics approach, which will be successfully reaching. So if I go to the slide, and as we see the robot arm, although it's a little bit jittery, does move towards the blue dot roughly right here, and it stops. So I'll maybe replay it again. I've heard that's a good idea. So we replay it. The robot is in fact moving towards roughly the target, something like right there. And so that's one of our approaches working successfully. And so just because I had the footage, here's also going to be a case of the other method failing. I should mention that this is not representative of like our empirical results. Both methods were fairly successful. But it's always good to show sometimes when things don't work. And so it's the same targets, same rough position of where we want the robot to move. But when I replay it, what we end up seeing is that, although it gets kind of close, so like most of the approximations are good, but at least around that particular point, the approximations with this method seem to break down and kind of diverge away from the target position. Yeah. So as we can see kind of here, the robot, it does move towards it. So fairly good approximations, but then it kind of wings out and doesn't seem to converge, at least with the allowed trajectory that we have. Yeah. And so these are just some conclusions that we had, which may not make sense. I didn't include the full experiment results, but basically compared to alternative approximations methods, our neural approaches were quite good. And our robot, as we saw, if we could use these things on real robots, which is always kind of conundrum with some robotics research. And we had some ideas of like, analyzing some stuff more specific to robotics problems like singularities, issues of redundant kinematics where the Jacobian is not as well conditioned. And there's some issues of just like more specific to even like visual servoing, where we kind of assumed that we had perfect alignment of the end effector location and where we wanted to move in the camera, but that might not always hold. Right. And so I think that's everything I felt like talking about. If there's any questions, let me know. And otherwise, thank you for listening and joining me this time. Question?
Okay, Michael, I'm going to ask about the inverse again, because I can understand how you might have a neural network with parameters and then you would train it, train that network to match the data in the one direction. But then I don't understand what, with the J, J is not a matrix, it's a neural network. And so what does J Dagger mean in this case?
Oh,
yeah.
So the neural network is a nonlinear operation, but when you differentiate through it, you get a linear matrix. So the Jacobian is still going to be linear when you differentiate with respect to the neural network. Like so, where is it? Yeah, so like the neural network itself may be nonlinear and doing its whole gobbledygook, but when we differentiate and do the actual operation, like taking the partial derivative with like the first output, second output, third output, we do end up getting a linear matrix. And so the Jacobian is linear after you've like differentiated with respect. And so then once you have that linear matrix, then you can invert that. But you're right, you can't. Oh, there's actually invertible neural networks are a thing, but that's out of scope of this particular problem space. So like so the J Dagger is on the output predicted from differentiating through the neural network to get these values. But like itself is not, but once you have it, it's not it is linear. I guess is what I'm trying to say.
But how about the other method?
For the other method? Yeah, so the other method is the same way where the output is well, so in terms of like implementation detail, what we are outputting is a vector. So just a large thing, then we reshape it to be a matrix, and that's technically the proper thing. So there's like a reshaping operations of this vector output, which we're going to treat as a matrix during our training. Does that make sense? I don't know if I'm just...
Yeah, the matrix is the output of the neural network.
Yes, the output of the so it's outputted by the neural network. Yeah.
Once you get the output, you can store it as a matrix. You can invert it or try to invert it.
So how about for longer trajectories? Do you have any issues with it sort of like accumulating errors over time? Because the Jacobian is a linear function. And so I'm not sure how well it would track unless you are doing some closed loop.
So the reason we like have these like global and using neural networks is because we wanted to get the Jacobian each of the positions. Whereas like if we took a finite difference and just kept the Jacobian fixed throughout the entire control, then I think, yeah, the approximation wouldn't be as good. And that's kind of some of the issues if you only use a single approximation. But what we're doing at every time step is recalculating the Jacobian. Does that make sense?
Okay, but like, does it sort of like wander off of the learned trajectories at some point and then start giving you garbage?
So I guess you're talking about if like we moved to parts of the robot space where we didn't have any training data and how good are the approximations there?
Yeah, does it wander off on its own?
Yeah, so we didn't actually, I guess, test like moving to parts where we had absolute training data. That's a good point. But yeah, so I would expect that if you move to regions where there was sparse training data for whatever reason, the approximations would not be as good as where you had a lot of training data. But that's, I think, almost comes down to like how well does your neural network generalize in the space. So I would expect that yes, in those regions, you wouldn't get as good approximations. The likelihood of like it failing to converge would be higher, but there's also some issues just with this general control law of like getting stuck in local minima and that as well. So I don't know if necessarily it's just because the Jacobians are the issue, as it could also be that maybe you just get stuck in a bad position and the robot won't move from there. There's also like limit. Yeah, does that make sense? Or
No, absolutely.
oh, okay. Okay,
Or
cool.
rather, yes, absolutely.
I have a question about the slide that's on the screen right now. So in this algorithm, when you're predicting the matrix, like what is the right error function to use? Like what about the matrix should the neural network predict correctly?
Oh, so like you're asking about the loss function?
Yeah, the loss function. Yeah.
Yeah. So yeah, honestly, I was always struggling with how to explain this. So the idea is that we're gonna kind of say that we're gonna fit like a system. We're gonna treat it like we're trying to fit like a linear model, basically. And so the delta xi's here, like if we got rid of the neural network and we just tried to fit this Jacobian term, we're kind of solving a least squares problem, basically, by regression. Where our training data is going to be all the nearby points to the corresponding training example that we want to fit on. So the reason we want the nearby points to it is because we're using the secant assumption where we're saying that for small differences between nearby points in like the space, so like in this diagram here, this lambda here, if they're for a small enough state, we're going to say we can draw like a straight line there, right? And so this roughly would equal to our equations of robotic motion. And so then we use a bunch of different data points at the surrounding point because to kind of, I'll say maybe like as a regularizing effect, because if you only use a single example, like lots of different Jacobians could fit through there, but like you want one fit that can roughly fit all of the nearby finite differences for that training example well. And because of that, the secant assumption and taking these finite differences, that's how we're able to fit and do supervised learning.
So I guess that answers the question of how do you convert your training data into a set of target Jacobian matrices. But what I'm asking is, how do you, what error function do you use between the predicted matrix from the network and the target matrix? Does that make sense?
Oh, we don't try to predict the target matrix directly. So when we do this operation, this becomes a vector. And so we're just matching two vectors here.
And so using like Euclidean distance between the vectors?
Yeah, just Euclidean distance. Exactly.
Okay. And the vectors are like the elements of the matrix, but reshaped to be a vector, right?
Exactly. Well, no, the matrix, it's a matrix vector product, and that's how we get back to vector to do this. Yeah.
Okay.
Just backpropagate through the theta is also in the index, right? So you will backpropagate the errors through the theta actually, right?
Yeah, exactly.
I have a related question. Have you tried to combine the two objectives? Because like you may want to do that, right? Like you want to fit a single function J, like a single function that's the kinematics function such that its derivative is also correct. So you have data for both, why not do the two at the same time?
So you mean using both objectives simultaneously? Or...
Like on the previous slide, I believe you had a different objective.
Oh, this one.
This one, yeah. Like, why not together?
Oh, actually, that is something I do want to do. Because something else I tried was that you can actually train the derivative of the network and you'll recover the original function, which I thought was kind of neat. And I just never made time to try it. There's actually some other stuff I would like to play with that, with like combining Broyden's update. Yeah, I think that there's some paper about this, Sobolov spaces or something, where they do exactly kind of this idea. So yeah, you're exactly right. We could just cram it all, have a single network. I really want to try that and play around with it. But yeah.
The other thing is that in the other objective, since you're using these k-nearest neighbors, some of these neighbors are going to be further away, some of them are going to be closer. And there is a bias variance trade-off here, especially if you're measuring things with noises, you normally would, right? Close by points are going to give you high noise, low bias, but you don't like them because of the high noise. And further away points, like the pairs are further away, then the bias is large. Maybe the variance is not really, or the noise is not really a problem. But all of this is kind of like, yeah, maybe some weighting that kind of expresses that you want to have some some nice middle ground rather than a k-nearest neighbor approach would be like a smoother way of doing that, or maybe it doesn't matter. Have you thought about this?
I actually haven't, but that's, yeah, because I guess if there's noise, like we could have the same point, but then like the neighbors are just like variations of the exact same thing, I guess. At least that's how I'm trying to understand your comment. Yeah, I haven't really thought about playing around with weighting the terms as much, but that's definitely something I might consider doing. Yeah, thanks for that. Thanks for the suggestion. Because I actually hadn't thought about bias variance trade-off in this approach. So you mentioned it. So. Cool.
So if there aren't other questions, I'm going to ask some more questions. So this minimization that's on the screen here, so how are we supposed to imagine that that's done? Is it done by gradient descent?
Yes, exactly. So you just do back propagation through the neural networks to update it.
Yeah, so I'm trying to figure out how it is that you can get the gradient of this objective. So theta, you're going to tell me how. It just seems kind of amazing that we can analytically determine how a change in theta will influence the inverse of the derivative.
Oh, you mean of this term?
Yeah. How does theta going to affect that term? Because theta is a function of f. It determines f, and then so from f you can.
It's a
Not here.
polynomial, right?
Not here.
Get a
Is it
This is a different
polynomial?
objective.
Sorry?
It is just a polynomial, right? Well, yeah.
Polynomial?
It's an inverse.
I mean, like of the entries of the J, like the determinant. Okay, so you have to have divide by the determinant. Okay, it's a rational expression. See, it's a smooth function. So TensorFlow takes care of it.
Yeah. So I think maybe the part of the confusion is like we're not using in this particular method where the output is just the Jacobian. We have no notion of learning the kinematics as part of it. So you can't recover the like kinematics from this particular approach. And there is some paper talking about how to calculate derivatives with pseudo inverses. Although I did just kind of rely on the fact that like, okay, if I take the pseudo inverse, is PyTorch going to do the back propagation for me so I don't have to worry about calculating the gradients? And it worked. So I was like, perfect, that's good enough for my purposes, which maybe is not the most clever thing to say, but that was my approach. Yeah.
So maybe clarify that these two are two different objectives. This one and the other one. Those are two different objectives and they lead to two different methods.
Exactly. As I think Chava mentioned, you could hypothetically like apply them on the same network if you like wrote out the derivative network and then, well, I guess you could also use, there's ways to like do it automatically, but yeah, so there, as we did it in this work, they're two separate methods, but you could imagine applying both objectives on the same network, I guess is what I'm trying to say. So in the first method, which is on the slide, we're just directly predicting the Jacobian without any fancy trickery. And then the other one, we're getting it by back propagation.
Okay, so let's look at the other objective and let's try to figure out how that is possible. So you change theta, that is going to change f, which is going to change j hat. And that is going to change that loss function, I guess. I guess it's possible. Apparently through a complicated way, but yeah. Okay, so you can actually combine all these objectives.
Yeah, and I think at least, yeah, when I was working at Borealis, they were doing exactly that. I think they called it Sobolov training, where you optimize the gradients, and it made sense in their context for like finance stuff, where they needed derivative information, the financial thing they do there.
So it's, I think if I understand properly, you're back propagating through back prop.
Yep. If you were to combine them, yes, I think so. Yeah.
Well, no, you're already doing it because
Yeah.
Because you're computing the gradient of the effect of theta on the back propagation of theta. Theta is determining f, and then you back propagate through f to get j. And now you're figuring out how a change in theta will affect j. Yeah, and so that's back prop through the back prop, and then that seems kind of wild, but then you're going one step further. You're back propping through not only the back prop of the neural network, but then through an inverse calculation on the thing that you got by back propping through the back prop. So that's pretty, it's surprising to think that that makes sense. But you're telling me you just somehow input it into TensorFlow and you got an answer.
Yeah. Maybe then, yeah.
Wild.
I'm not sure I understand why that is backpropping through the backprop, because like isn't the output of the network like if you were doing that with the kinematic network, I think it would be, but the output of the Jacobian network is just a Jacobian, right? So you don't need a one backprop step to go from the kinematic function to the gradient function. I'm not sure if I'm making sense.
For this objective,
Yeah.
you kind of do. So you use one backprop for training, another backprop for deriving the Jacobian.
Okay, yeah, right, in this objective, but not the other one, right?
Not the other one. But then I think Rich is considering the case where you combine, as Java suggested, if you combine all three together, then
right,
I think that scenario appears.
I see, yeah, thanks.
It was the one you actually did. The one you actually did is you it's an optimization on an objective that involved the gradient and the inverse. Yeah, all these fancy words. F from F, you backprop through F to compute J. And then you talk about the derivative, the gradient of J with respect to theta. Okay, and J is not an immediate function of theta.
No, we don't do it here. If you are asking what we did in this objective, once we get J, that's it, we are done. You don't take.
No, because you've got to find the minimum of a term that involves J and J inverse. And to find that
No, that's a different approach. That's what I wanted Michael to clarify, that's an alternative method. In this method, we don't do that. The other objective you saw, that's not used here.
Oh, so you didn't do that.
Oh,
right.
You didn't do oh, sorry, that was confusing. Sorry,
yeah, we will do
entirely separate. Yeah.
Take Java's suggestion and combine all three, basically all two. But these two right now, the things that we did here, these two are separate. Here we backprop through F to train. And then when F is...
You just trained F to be correct.
Right.
Yeah.
Yes, sir.
Didn't do anything with the J's. Okay.
Later, but we derive J though. We need J. So we derive J by taking the derivative of F with respect to Q.
Yeah. They didn't do the other one.
They didn't do the other one. I thought they did the other one.
You're saying the one on the next slide or whatever it is, where you have the No, the one with the
This one.
With the objective?
backup one. Yeah,
Yeah.
this you didn't actually do this.
No, we did. That's the alternative
Yeah.
approach. These
Well,
two
well,
are
here-
two different
Yeah.
approaches.
You have to get the gradient of this objective, and that is a gradient of something that is only computed through backprop. Right. So that's the surprising bit.
So here there is no F. We don't have an F network here. This is an alternative approach where we don't actually make F correct.
Well, how do you get J? How is J a neural network?
J is the output of a neural network.
Okay,
Neural
so
network takes,
then
yeah.
my question comes back.
Yeah.
Then J is not going to be linear.
Well, the output is,
Excuse me, J, the function J is not linear. Because it's a neural network. And then what is J Dagger?
I mean, it may be like if you think of like a rotation matrix where there's like cosines and sines and stuff, the independent operations themselves are like nonlinear. But then once you like get the matrix itself, that's where the rotation itself is linear. That's kind of, I think, the idea of what's going on here. So yes, the neural network in fact is nonlinear. There's tanh, ReLU, whatever's going on. But the output itself is just going to be a matrix. So we're just using a neural network to produce matrices. And so that output itself is going to be linear, which is how we're able to do these calculations and take the inputs. So we're not, so this is just the output prediction of the network itself. Does that make sense?
I think it is a bit confusing that these two probably should have been clarified, that there are two different networks for two different approaches. Both are not used in the same approach. We either train F or we train, maybe we shouldn't call it J theta. We should call it something else which outputs J, right?
Yeah.
It sounds like
That
Jacobian is
notation,
the network.
Yeah, that's understandable. I guess with this notation, that's
it's let's call it G. G is the network which outputs J.
yeah. This is bad notation on my part.
So we either train G or we train F. When we train G, it directly gives J as an output. And when we train F, we take the derivative of F further with respect to Q to get J.
I was curious about like this interesting thing you said, that training a network on the points also gets the gradients basically correct. I was just wondering if you had a chance to test that hypothesis, like to what extent is that true?
Sorry, could you repeat the question? I was looking at the chat.
Yeah, sorry. Yeah, so you said that there's some literature on neural networks that says that if you train the network to get point estimates correct, then usually you get the gradients correct as well. If you're trying to fit some smooth function, I assume. So did you test that hypothesis? Like, do you know, like if you train the kinematics network, or maybe, yeah. Yeah, so I guess what I'm saying is, so if you train the kinematics network and then you check that the gradient is good for the task that you're doing, which is moving the robot arm around, but do you know if that actually produces like correct gradients, correct Jacobians?
Oh, yeah, we did that experiment. I have a slide for it. So where is it? Oh, I don't have a slide. I lied. It is in our paper though, where we basically just compare the ground truth Jacobian to what is produced by the network. And yeah, the gap with some of the approaches is much smaller compared to alternatives. So we just took the Frobenius norm. How close is this to the ground truth, to the kinematics one? Yeah, all my fun slides.
Interesting. So you don't actually need to train the whole, you don't need to train, yeah, you can just use the error in the estimate. That's really interesting. Thanks.
Yeah, exactly. I guess this, where's the slide? Yeah, so this is kind of the same idea, right? Where like it's one-dimensional problem, and then we could just compare what is the gap between cosine and the backprop of estimate. And so just visually we can see like, oh, it looks pretty good. But
And you know how dependent this is on the neural network architecture? Like if you make the neural network wider or deeper or whatever, does that change?
We found that using the like the activation function makes a difference. Like with ReLU, you can't. I think there's like you can't keep going higher and higher order derivatives just because like you're doing local linear models and eventually they'll flatline. And TANH actually worked better in practice by like a notable margin, like I think a 10% improvement in terms of successfully reaching targets. So we did find that architecturally activation functions do make a difference. And so like sparsity kind of affects, well, I'll say sparsity just because ReLU is kind of sparse, did kind of negatively impact performance compared to alternatives.
Okay, interesting. Thank you.
Yeah. You can also do this with radial basis functions. There's a paper that talks about their ability, or they're just not more neural networks